Today we'll talk about formal languages before we get into finite state automata, and these will be probably the last two videos in the series. So, what is a formal language? Well, we all know what a language consists of. It consists of alphabets, it consists of phrases, idioms, tonality, meaning, intention, all that stuff. Now, formal languages are a little bit different. They have alphabets, they have rules, and they have words. So, how do we define an alphabet for a language? This is the first thing we need to build a language. Well, we symbolize all alphabets with a nice little capital sigma here. I want a nice fine point for this. Sigma. And we let sigma be a set of acceptable characters. So for instance, for computers with binary, we have the acceptable alphabet being zeros and ones. But perhaps if you are speaking English and writing English words, you want all the letters up to Z in your alphabet. And perhaps maybe you really only want to work in vowels because you don't like consonants. So you have A, E, I, O, U, and maybe you really love the Greek letter phi. So you throw that in there too. You can define an alphabet however you want. So, what happens when we take an alphabet and we put an operator on it called the star operator? Well, the star operator, basically, instead of having an alphabet of acceptable characters, this sigma star is a set of all possible strings or words in the language. So, if we have sigma is just A and B, then this sigma star is going to consist of, well, the empty string, which we have here called lambda, and this is the empty string. So this is just not putting in any word, leaving it blank. You'll have A, you'll have B, you'll have A and B, B and A, B and B, and then you'll have AAA, and it'll go on forever. It basically will not stop. It's an infinite set. Of course it's countably infinite because it's very easy to count how many possible strings there are at each step. Of course the order matters. For instance, the word dog in English is not the same as the word God. So clearly order matters. It's the same as that. And that is a very interesting property of finite state machines, or sorry, not finite state machines, formal languages, because obviously there's some counting and stuff you can do in here. You can do a lot of stuff related to functions, which we'll see next time. But what I really want to get at are actual languages, because we've just sort of been talking about alphabets, and languages are a little bit interesting. Because we let L be our language, and L is always going to be a subset of our sigma star. So we can reject certain things. So let's have sigma equal just A and B. And say I want my first language here to be just either an empty string or anything that starts with an A. In fact, it has to start with an A. That's the only restriction, is that it starts with an A. So it can be whatever it wants, but it has to start with an A. And this will go on forever. So we can write this as, say, the set of, let's call it strings S. Actually, we shouldn't call it strings. Standard notation is W for, I guess we call it a word, where W begins with an A. So we can have a language like that. Perhaps we want a language too, which, should not include sigma, or not include lambda, should not include the empty character in that case. That would be my bad. Or the second language here, where say, what if we want it so that words have to have an even number of A's? So we say W or W has even number of A's. So acceptable words in the language would be like ABBA or ABBA or say A or even just B, because it does have an even number of A's, it's 0. So we can construct these languages to do and accept basically whatever we want. Sort of interesting, in fact, if you think of actual language, or rather just the set of words we have in a language. We have some rules in English, like, for instance, ST and R together are fine, but you can't have the letters K, P, R, S, T, and V all together in one clump, because we can't really pronounce that. So we have rules like that in our language too. But there is one thing, perhaps, well, I don't want an English word to consist of more than 30 characters. So, when we take our word, we can check the length of the word by doing the absolute value. So, in this word, it would produce the number n. So, if we have AAB, this length is 3. If we have ABA, again, it equals 3. So, pretty simple. What you should know is that the length of the character lambda is 0. So if I had as a trick question A lambda B lambda lambda, what is the length of the string? Well, it's 2. So a little bit tricky, but that's basically lengths of strings. The most important part of formal languages are rules. So we can define our rules recursively. So we can say, okay, let s equal lambda. So we start with an empty string. And given s, we can have the character ASA. Given s, we can have BSB. And given s, we can have, AAS. So these are sort of recursive things. So if we start with lambda, we can choose one of these to go to. So let's say we have lambda, and we'll call this rule 1, rule 2, rule 3. What we'll do is we'll use rule 1, and we're going to get AA. Now what we can do is we can use rule 2, and we can get BAAB. Let's go a little bit crazy, and now we'll use rule 3. So we'll get AABAAB. And you can specify your language with these rules. Now, that's pretty much all the basics we need for formal languages. Next time we're going to go over finite state machines, which is where we do this stuff with graphs and pretty drawings, and it's going to be really fun. But you do need to know the fundamentals and just how these work. This is something that is, I'd say, probably a very, very easy mathematical concept to understand at a very basic level. So, a language, L, basically consists of an alphabet, which we call sigma. It consists of rules, which we use as a lowercase delta. And I guess what it does is it takes some final accepted states, which we call F. And that would be a nice little language there, which probably should be in pointy brackets. But that's formal languages. If you have any questions, as always, leave them in the comments below, and I will get to them as quickly as possible.